Yeah, good morning, everybody. Welcome to the morning session. And I request Akshay Singh to chair this.
Hi, Priya. Thanks for this opportunity to be the chair. The first talk in this session will be given by Emanuel Tutuc, who's actually from my alma mater, UT Austin. And Emanuel, please.
Thank you. I wanted to thank the organizers for having me here and for hospitality. Today, I'd like to discuss, as the title suggests, the topic that's called tunneling and interlayer coherence in twist-control van der Waals heterostructures. And we'll discuss what do we mean by this, and also we'll discuss the experimental techniques and what interlayer coherence, what do we mean by interlayer coherence. Before starting, I'd like to acknowledge the people that did the work, students in my group, Kenneth Lin, Will Berg, Yimeng Wang, and Kyung Kim. Nitin is a student of my colleague Frank Register, and also collaborators at UT and elsewhere, without whom this work would not have been possible. So we have seen already in this workshop a discussion on 2D materials, particularly graphene. Just to remind ourselves, these are carbon atoms in a honeycomb lattice. It has a linear energy momentum dispersion and a Brillouin zone that is hexagonal. And this will be important in the ensuing discussion on tunneling. Two other materials that we'll be using here as supporting actors are hexagonal boron nitride, which has the same crystal structure, except that on one sublattice we have boron, and the other sublattice we have nitrogen. This is an insulator, an atomically flat insulator that can be exfoliated similar to graphene. And transition metal dichalcogenides that have a chemical formula MX2. M is a transition metal, X is a group 6 element. And these are semiconductors with a band gap of around 1 electron volts, and they become direct band gap in the monolayer limit. We will use transition metal dichalcogenides as tunnel barriers in this discussion. So, the outline of the talk, we'll discuss twist-control van der Waals heterostructure, momentum conserving tunneling in double layers, and then interlayer coherence in twist-control double graphene monolayers. And this basically illustrates, this is a transmission electron micrograph that illustrates a double layer, which is a heterostructure consistent of bilayer graphene, tungsten diselenide bilayer graphene, and encapsulated in hexagonal boron nitride. All right, so we have heard in this workshop quite a bit about twisted heterostructures, twisted structure, moire materials. This is a field that is relatively big now, and I'm showing here snapshots from some of our work on the twisted bilayer graphene, twisted double bilayer graphene, twisted double bilayer graphene, where we are using a monolayer graphene in order to measure the chemical potential. And this is twisted quadrilayer graphene, which have interesting properties like superconductivity, and correlated insulators. This field was really spearheaded by the discoveries of superconductivity in twisted bilayer graphene by Pablo Herrero's group at MIT. And another discovery that came unexpected is that of orbital ferromagnetism, again in twisted bilayer graphene, when the hexagonal boron nitride is aligned with one of the graphene layers. So those were unexpected discoveries that really added momentum to the field of moire materials. If you want, the magic in this system is the fact that the bands are flat at the magic angle in twisted bilayer graphene, and that basically enhances the role of electron-electron interaction, as we've seen from speakers already in this workshop. What I wanted to do in the ensuing discussion is to perhaps highlight another angle that has its own magic in twist control van der Waals heterostructure, and that is the angle 0. Okay, and to do that, I'm going to take a step back, and I like to basically survey here flavors of excitons that primarily colleagues in photonics they study, depending on how they occur, depending on the band alignment and the systems that they study. We can picture direct excitons. This is basically electron-hole pairs in bands aligning momentum space in the same material. We can picture spatially indirect excitons. These occur in hetero bilayers, where the electron sits in one layer and the hole sits in the opposite layer. We can picture equilibrium excitons, and these occur when a conduction band aligns, overlaps with the valence band, and there are systems like indium arsenide, gallium antimonide, tungsten ditelluride, and also double bilayer graphene or double monolayer graphene, as I'll show in the following. And one particular case of equilibrium excitons occurs in a double layer that is actually subject to a perpendicular magnetic field. In a perpendicular magnetic field, the states in the conduction and the valence band, they form Landau levels. Those are flat levels with a high degeneracy. And if we picture here a case where we have Landau levels in the two layers and the Landau levels are half filled, we can picture pairing a particle in one layer with a vacancy in the opposite layer, and that forms a spatially indirect. So that forms an equilibrium exciton where the electron sits in one layer and the hole sits in the opposite layer. And this system is interesting because we can represent the state using a BCS-like wave function, and I'm showing this representation here. We add the particle in one layer, the particle in the opposite layer, and there is a phase factor right here that is reminiscent of the BCS wave function. So these excitons, they would condense at low temperature, and they would give rise to interesting experimental signatures like Josephson-like tunneling. So to see that and to see perhaps what controls this Josephson tunneling, let's go back to a textbook where we have here two superconductors. They're separated by a tunnel barrier. If we have we can build a simple phenomenological model where we assign an energy cost to move a Cooper pair from one superconductor to another. That is EJ right here, the Josephson energy. And we can show that the current that flows from one superconductor to the other basically is controlled by the following phase difference between the two superconductors. So we have a critical current here times sine of the phase difference. And one thing to note here is that this critical current is proportional to this energy that's required to move one Cooper pair from one superconductor to another. I should say that I should emphasize that this is not really a tunneling, hopping energy, because if we look closer at the Josephson energy, that's proportional to the tunneling square. And we can build a simple phenomenological model for this particular case, and we can show that the current also follows this Josephson-like tunneling relation, where the critical current is proportional to the area and to the hopping energy between one layer and another. So a key take-home message is that in this exercise right here, the tunneling, the single particle tunneling from one layer to another is important in controlling this Josephson tunneling. Okay, and this Josephson tunneling has been observed and studied extensively in gallium arsenide double quantum wells, both electrons and holes, and it's a very, certainly very interesting phenomenon that testifies to the coherence and to this wave function used in representing this equilibrium exciton condensate. Okay, so given this, we would like to test if we can stabilize something like this in van der Waals heterostructures. Okay, so I'm gonna with this in mind, with the fact that the tunneling is very important in stabilizing this Josephson tunneling, single particle tunneling, I'm going to take a little detour and remind ourselves that in heterostructures, let's say the ones that are grown epitaxially by molecular beam epitaxy, there is a registration between the atoms in the atomic layers that are built upon each other, okay? And growers would take those registrations for granted, and we can use formalisms like the envelope function in order to represent the wave function in a heterostructures, right? And because of these registrations, the momentum is a good quantum number from, let's say, one quantum well to the other quantum well. The momentum in the sort of in the perpendicular to the growth direction, okay? The in-plane momentum. That's not necessarily the case for van der Waals heterostructures unless they're twist control. So it's important in a van der Waals heterostructure to basically, if we want to control the tunneling from one layer to another, to actually have twist control, to ensure that the momentum is a good quantum number from one layer to the next. So first of all, how would we test something like this? Okay, so the way to test it is to use resonant tunneling, and the basics of resonant tunneling can be understood using this picture right here. So let's picture that we have electrons in two layers. We have parabolic bands, and momentum is a good quantum number. If we tunnel from one layer to another, and the bands are mismatched in energy, if we conserve momentum, we don't conserve energy, and if we conserve energy, we don't conserve momentum. So if momentum is a good quantum number, tunneling is suppressed. Conversely, if the bands are aligned, then both energy and momentum conserving tunneling is possible, and tunneling is allowed. The signature of this in experiment is resonant tunneling that is gate dependent, combined with negative differential resistance. So if this condition is satisfied, there is a large conductance, and if this condition occurs, basically the tunneling current drops. Okay, so these are data in gallium arsenide double quantum well. And the current voltage relation can be captured by this analytical formula proportional to the density of states. There is a Lorentzian right here. There is a broadening of the quasi-particle state. And very important, there is the single particle hopping energy from one layer to another. So this experimental data, such as this, could be converted so we can actually back out an interlayer tunneling energy. There's been extensive work done in gallium arsenide to the electrons, double quantum wells, gallium arsenide to the holes, again, double quantum wells, and then subsequently in double monolayer and double bilayer graphene. And I'm going to discuss these two topics in the remainder of the talk. Okay. So I said earlier that momentum has to be a good quantum number in order for tunneling to occur, because if the momentum is not a good quantum number, moving from one layer to another basically suppresses tunneling. So in order to observe resonant tunneling, we have to ensure that the crystallographic axes of the two layers are actually aligned, okay? Because if they're not aligned, again, tunneling becomes suppressed. At small angles, it still occurs, and we'll see an example of that, but if they're mismatched by a large angle, tunneling is completely suppressed. Okay, so how we do this, we basically use large grains. We split them in two using either lithography and etching, or maybe FM cutting. Sometimes we use laser cutting, but the bottom line is that if we use a large grain and we split them into two or more segments, we could stack these sequentially, and if the layer crystal axes are aligned at the onset, they will be aligned in the ensuing heterostructure. And we can keep them aligned, or we can introduce a control twist if we desire to do so. Okay? So we would use a hemispherical handle that's coated with the polymer, and then we would choose the flakes that we want to stack, and we would proceed with the stacking. This is done with different setups. We started using a setup that was built around the commercial mask aligner, and then we subsequently built one that is entirely computer controlled with XYZ and rotation stages. And many other groups have these setups as well now. So we would basically proceed as this. So let's go through the exercise. We pick up a stamp. This would be a dielectric that will become the top dielectric of the heterostructure. And then we have two layers. It was split in two. Pick up the top one. And then we can pick up the second one with a twist or without a twist. Let's say for the sake of illustration, we add the twist here and we stack them. And we have a twist control heterostructure in the manner shown here. Now, the heterostructures are a bit more complicated because we have interlayer tunnel dielectric, we have top and bottom dielectrics, but that's in essence the basic of how we stack these structures. So let's look here at double bilayer graphene separated by tungsten diselenide. This is the schematic. These are materials. The tungsten diselenide is one of the higher mobility transition metal dichalcogenide, and also has a good band alignment with graphene. So that's why we chose it in this exercise. So let's illustrate the sample fabrication. Pick up the top dielectric. So these are the two graphene flakes that have been etched into mesas. These are the contact arms. Pick up the first one. Pick up tungsten diselenide, and then pick up the second one, and then we would basically pick up the bottom dielectric or land it on the bottom dielectric, and this is the device with metal contacts to the top and bottom layers. So this is the device that would allow 2 and 4 point measurement, and we can do tunneling measurement between the two layers. Let's go ahead and do this. This is a transmission electron micrograph of the stack. So if we do a tunneling measurement where we use 2 contacts to inject the current and 2 contacts to measure the voltage, we see something like this. So this is the negative differential resistance. This is gate tunable resonant tunneling with negative differential resistance. This is not visible right here due to a circuit instability. This has to do with the balance between the contact resistance and the negative differential resistance. But the data is, it has the negative differential resistance. This is data acquired at room temperature. So already this shows that this phenomenon is actually robust. So we can understand this data quantitatively. So we can build a model that has a transmission from one layer to coefficient from one layer to another. And this transmission coefficient basically makes use of the spectral function that are shown here times hopping energy that we chose it to be. So this broadening that you see here, this gamma and T are the 2 parameters that are used in this model, just 2 parameters. So this is the hopping energy from one layer to another. That's important. And this gamma is a quasi-particle state broadening that can be determined by comparing the experimental data and calculation. In this particular case, you see here the experimental data and the calculation. The experimental data are the symbols, calculations are the solid lines. Very good matching both at low temperature and room temperature. Hopping energy would be in the micro electron volts, and then the gamma would be in the few milli electron volts for this particular structure. But bottom line is that this technique, we can have resonant tunneling due to the twist control, and we can also back out this hopping energy from one layer to another by using a comparison between experimental data and calculation. Okay? So we can, if we were to do a set of measurements such as this, but at different top gate voltages, we can build a contour plot that's shown here, okay? And the calculations are shown here. What you see here, the main feature is the resonant tunneling that has a high conductance. The band alignment that are shown in the bottom here, it basically shows the band structures of the 2 layers align. Interlayer bias controls the separation of the Fermi levels between the 2 layers, okay? When we are at a finite interlayer bias, the Fermi levels are separated, okay? The bands are aligned along this line. And there are a few other features in this graph that are worth mentioning, and that is the unlike band tunneling. So if we align, for instance, when the conduction band and the valence band intersect, if the Fermi level is aligned with that intersection point, there is another channel, there's another set of states that conserve energy and momentum, and that gives rise to these resonances that we call unlike band tunneling, okay? But the bottom line is that the experiment and calculation agree very well, and again, in this case, we inherently assume that the momentum is a good quantum number in both layers because the layers are twist aligned. Now the question is, how good is the alignment? Okay, so we can do an experiment where we apply an in-plane magnetic field between the two layers, and when the electron tunnels, it acquires an extra momentum, okay, due to the Lorentz force. So that would be shown here, and the consequence of that is that the resonance would actually split into two resonances. So if before a resonance occurs when we align the bands, if we mismatch the bands in momentum space, we can get a sort of a high conductance either in this situation right here or in this situation right here. Okay, this is a negative interlayer bias, this is a positive interlayer bias. Okay, so applying an in-plane magnetic field would split the resonance, and we see this experimentally 0, 5, 10, 14 Tesla. Okay, they're very clearly separated at 14, 10, and even at 5 Tesla. And to give you a sense of what 5 Tesla means as far as momentum, 5 Tesla, the mismatch in momentum at an in-plane magnetic field of 5 Tesla is equivalent to the momentum mismatch one would get at 0.04 degree if there was a mismatch of twist of 0.04 degrees between the layers. Okay, so in essence, the layers are good. They're well aligned. Okay, to the best, to a very good accuracy. Okay, so let's go back to the problem that we set out to explore, and that it would be the exciton condensate in double layers in the quantum Hall regime. Okay? And the signature again that we want to look for is this Josephson-like tunneling when we have two Landau levels that are half-filled. Okay? So the system that we will explore consists not of double bilayer graphene, but actually of double monolayer graphene. Okay? The physics, again, can be understood using this BCS-like wave function. The models are more complicated than I would represent, so I'm just pointing out these references right here. They make use of the pseudospin, the layer degree freedom as a pseudospin, and there is a phase that basically is the phase here that it's the one that we show in this BCS-like wave function. But if the calculated tunneling currents in a model like this are proportional to the area, they're proportional to something called pseudospin stiffness that's controlled by electron-electron interaction, but very importantly, they're controlled by the single particle hopping energy from one layer to another. Hence, it's very important to have a good handle on this hopping energy from one layer to another if we want to stabilize an exciton condensate in double layer in the quantum Hall regime. Okay? So the system we will be studying consists of two monolayer graphene separated by hexagonal boronite as a tunnel barrier. It's similar to the structure we just examined before, except that instead of bilayers, we have monolayer graphene, and the tunnel dielectric is not tungsten diselenide but hexagonal boron nitride. And hexagonal boron nitride tends to have a lower conductance, tunneling conductance for a given thickness compared to tungsten diselenide, and that has some advantages experimentally. Okay, so in this particular case, we have a device where the tunnel barrier is 5 monolayer thick hexagonal boron nitride, And these are the measurements, these are the calculation, and what you see here, this is the direct tunneling resonance from one layer to another when the bands of the two monolayer graphene, the Dirac cones, are aligned. Okay? So we can have a situation like this where the bands are aligned and the Fermi levels are almost at the same level. So that would be at zero interlayer bias, or a situation like this where again the cones are aligned energetically, but the Fermi level are split, and that would be at a finite interlayer bias. Okay. And the calculations using the same model, they match very well the data, and we can back out the interlayer coupling. It's 1 microelectron volt, very small in this case, and the broadening is relatively large in this particular device, but as you'll see, is not a showstopper. So now let's take this device and place it into a perpendicular magnetic field. The Dirac cones in each layer, okay, will become Landau levels, discrete Landau levels, discrete levels with a microscopic degeneracy. There would be one at zero energy, and then there would be indexed by an orbital integer, 1, 2, 3, and so forth on the electron side, and 1, 2, 3, so forth on the hole side. It pays to note that these Landau levels are fourfold degenerate because of spin and valley. Okay, so let's now go ahead and probe the conductance, the tunneling conductance of this device in a perpendicular magnetic field. This is 14 Tesla as a function of top gate and bottom gate. And what you see here, we have areas of large tunneling conductance along the main diagonal of this contour plot. And that occurs when we are in the middle of a Landau level. So this would be n equal to 1 in top and bottom layer. This is n equal to 2 in top and bottom layer. This is n equal to 3 in the top and bottom layer. And because of the large density of states, we have a large tunneling conductance. Now, we can actually calculate the filling factors in the top and the bottom monolayer graphene. And I'm showing here the constant density contour plot. So this is the 0, 0 sector. Each monolayer graphene is at the n equal to 0 orbital. Landau level 1, 1, 2, 2, 3 t, minus 1, minus 2, so on and so forth. So good agreement between the experimental data and calculation. Now the interesting thing is that let's zoom in into this area right here. So this is the 0, 0 sector. We are in the n equal to 0 Landau level, okay, in the top layer, and n equal to 0 Landau level in the bottom layer. So if we were to zoom in right there, we see a set of peaks right here that show high tunneling conductance when the filling factor in the top and the bottom layer is half of an integer. So 1 half, 1 half, 3 half, 3 half, minus 1 half, minus 1 half, minus 3 half, minus 3 half. In combination here, these are in balance, minus 1 half, plus 3 half, plus 3 half, minus 1 half. So this is indicative of this phenomenon that we wanted to explore, where if indeed pairing occurs when the Landau levels are half filled, we would see Josephson-like tunneling. Now, what I'm showing here is simply a large tunneling conductance. This is not Josephson-like tunneling. So let's explore this a bit further and see what we learn. A high tunneling conductance can also occur if we have a high density of states. And we can picture perhaps splitting the lifting the fourfold degeneracy in the two layers due to electron-electron interaction. And that should also give rise to a high tunneling conductance at half filling. Okay? And what I'm going to argue in the following is that that's not the case. Okay? This is not due simply to a high density of states in the top and bottom monolayer graphene. Okay, so what we'll do, we're going to park the gates somewhere around one of these high tunneling conductance, and we will measure the tunneling characteristic. So we'll park the gates at a fixed filling factor, and we'll do an IV tunneling measurement and plot here the DIDV, the tunneling conductance, as a function of interlayer bias. And we'll do this measurement at a bunch of gate voltages. So what I'm summarizing here, I'm summarizing data that is taken by detuning the layer filling factor in the same direction. So we would add electrons to the top and bottom layers. And this is a case where we would take electrons from one layer and move them to the other layer. In other words, we would do these measurements, or at least this data set is acquired by basically going a set of gate voltages in this direction or in this direction. What you notice right here is that we have a high conductance peak that remains parked at zero interlayer bias, irrespective of the filling factor. So we have a zero bias tunneling peak that is immune to changes in the layer density or the layer filling factor. If this tunneling peak was due to simply to a high density of states, it should move with the layer filling factor. Okay, so we did measurements at a variety of sort of high conductance points. So this 3½ 3½ 3½ minus 1/2. So that would be 3½ 3½ 3½ minus 1/2. So these are these two. And in essence, we see a zero bias tunneling peak in both cases that is immune to layer filling factor variation. Another thing to note is that if we were to look at this peak, it's very narrow. It's significantly narrower compared to the tunneling peak that we measure at zero magnetic field. So here we have a interlayer, a tunneling peak is that shown here. And for a point of comparison, the red trace is the one at zero magnetic field, and the black one is the one that's measured in a magnetic field at these half-field Landau level. So we have a zero bias peak that is immune to variation of layer filling factors, and it's also significantly narrower than the single particle tunneling peak at B = 0. So this basically signals this Josephson-like tunneling because theoretically it's also expected that if the layer filling factors were to be detuned, the zero bias peak would stay exactly at 0. So let me do one other consistency check right here. What we'll do is we're going to go to a situation where we align Landau levels. So we would align the n = 0 Landau level in the top layer with the n = 1 Landau level in the bottom layer, and necessarily the -1 is going to be aligned with the 0 Landau level. And we would see a tunneling peak right here, okay? And these tunneling peaks, they occur when we basically have a high density of states to tunnel in and out of. Okay? So in this case, we have the n = 0 Landau level, which is filled, and this one, which is empty. And if we were to zoom in on this, this changes significantly, noticeably, with changes in layer filling factor. So this is simply a consistency check that says that if you have a tunneling peak that stems from simply a density of states, it should respond to a gate bias. And this is different than this tunneling peak that is parked at 0, irrespective of the layer filling factors. So this is certainly a strong indication of interlayer coherence that occurs in double monolayer graphene. And we have additional data that basically confirms this Josephson-like tunneling. And one other point that I wanted to make is the following. We discussed earlier the role of twist control in order to be able to stabilize single particle tunneling from one layer to another and to be able to quantify it. Now, let's say that we have a device that has an inherent twist between the two layers, and this is a device that basically didn't go according to plan. The twist was not basically, we didn't aim for this angle, but that's how it came out of the fabrication. So there's a 1.3 degree twist between the two layers, and there are ways that we can quantify that using measurements at zero magnetic field. And if we were to do a measurement of the tunneling between the two layers in high magnetic field, this is the device we just examined where the layers were aligned, and this is the device with the 1.3 degree twist. And you see right here in the n = 0 sector, there is basically no tunneling. The tunneling is completely suppressed. Why is that? So to answer this question, we can just look at the Dirac cones shown here. So these Dirac cones are now displaced in momentum space because the layers are twisted with respect to each other. As a result of the twist, the n equal to 0 Landau levels basically are, they completely, the orbits completely don't intersect in momentum space. So we can have some tunneling between higher Landau levels. So in this case, for instance, we can, the n equal to 1 Landau levels, they do touch, and there would be a tunneling right here, and there would be an enhanced tunneling between the n equal to 2 levels. But there would be no tunneling between the low-lying, the n equal to 0 Landau levels. That's because of this twist between the two layers. So twist control is particularly important in this case if we want to stabilize or if we want to examine the Josephson tunneling between the two layers due to the pairing of electron holes in the half-fill Landau levels. So role of the twist control is important because otherwise then there's basically the single particle tunneling vanishes due to this momentum mismatch. Yeah. Yeah, that's a good observation. I would assume that this is basically due to device imperfection. Yeah, it's. I don't think that there is any. Yeah. Yeah. These measurements are all done at 1.5 Kelvin. So the resonant tunneling survives well to room temperature. The Josephson tunneling, it vanishes. I don't have the data here. It vanishes at about 30 Kelvin. I think I have some data in the backup slides. Yeah. Right. So the Josephson tunneling, it vanishes at, I would say, 30 Kelvin. Okay. If it, I don't know that we have a, certainly I don't have a quantitative explanation of that. I should say that if we were to look at the parameter that controls the inter versus intralayer interaction in this system, it's D over LB. D is the distance between the layers, LB is the magnetic length. The lower the better, okay? So this is a relatively low, D over L is below 1. The D over LB that, you know, where the value at which this Josephson-like tunneling in the electron hole pairing should occur is somewhere around 2. So we're well below that transition. But if you're asking the question, is that do we have a direct, you know, a quantitative understanding of what the critical temperature should be at a given D over LB? My answer would be no. And that has to do with the fact that if we were to, let's say we want a low D over LB, we would lower the magnetic field, but what we see experimentally is that if the magnetic field is sufficiently low, this disappears, and that's due to disorder. So, yeah. I will sum up here with basically with a representation of these states that we see that have half-fill Landau level where we see Josephson-like tunneling, and there are two sets of those. Those would be when we have equal filling factors in the two layers, okay? And then there is another set where the filling factors have a difference of 2, okay? So that would be here 1/2 minus 3/2, 3/2 minus 1/2. How do we understand it? So if we picture the fourfold degenerate Landau level, and then we lift this degeneracy with the valley splitting and with the spin splitting. The valley splitting is accepted, it's known to be larger than the spin splitting in monolayer graphene. There are a number of studies that point to this. Then we can picture this fourfold, the four Landau levels in the n equal to 0 sector as this. So k up, k down, k prime up, k prime down. And we can picture the coherence between these Landau levels in the manner shown here. What about the case where we have a filling factor difference of 2? We would align k would spin down with k prime would spin down. And what this suggests is that in tunneling, the spin is conserved. This is not surprising, but what it says is that the picture that we see experimentally is consistent with spin conserving tunneling. Okay. Valley should be conserving tunneling as well, because valley is momentum. And the way we explain the fact that we don't see is that basically the states are inter-valley coherent in monolayer graphene. And that's also consistent with studies, STM studies in monolayer graphene. Okay. So with that, I'd like to put up the summary and be happy to take your questions.
Question is regarding the choice of materials. So you showed bilayer graphene with WSC2 and then this experiment is monolayer and HBN. So if I remember it right, your PRL to 2018 work, you did see when the equal charge carrier densities in both layers, there was signature of enhanced tunneling, which was probably without magnetic field, a signature of a similar excitonic thing. So what made you change to this material system, and would you have observed a similar thing in bilayer WSC2?
So let me, right, this is a good question. So let's ask the question, would we have observed the zero field enhanced tunneling if we have electron and holes in the two layers? The answer would be, I don't think so. And I'm gonna, or it will be more difficult. And let me explain why. So if we go back to this system right here. So this point right here is where we have equal electron and hole densities in the two layers. This is called the unlike band tunneling, okay? And this occurs when we have this picture right here. We have a conduction band in one layer and the valence band in the other layer, and the Fermi levels are basically aligned because of the zero interlayer bias. Unlike band tunneling in double monolayer graphene is suppressed. We see this experimentally, and I could give an explanation that is, I'm not sure is the correct one, but it could be one explanation is that so if we were to take the cones in double monolayer graphene, and if we were to invoke pseudospin conservation, we would get suppressed tunneling in a situation like this. Okay, it's not the case when we have bilayer, okay, but in a nutshell, unlike band tunneling, in double monolayer graphene is suppressed. And that is seen right here, or at least we don't see any other feature except for the main tunneling peak, okay? Now, for the other question, like would we have seen, can we see Josephson-like tunneling in double bilayer graphene in a perpendicular magnetic field? We haven't done the experiment, but my suspicion would be, yes, it should be there. But until we have that experiment done, I cannot say for sure. Right, so I don't think that there is, the one thing that HBN is a slight advantage of HBN versus WSC2 is that it ensures, so if we go to data in double monolayer graphene, the tunneling currents are relatively large. So there's a large tunneling conductance. And if we have a large tunneling conductance, the assumption that the two layers are equipotential is not very good. So if we want to do a 4-point measurement where we basically assume that the two layers are at the same potential, it pays to have a thin tunnel barrier with a high resistance. So there is a marginal benefit for having HPN. Now there's complications with HPN as well because it has a, you go up on one monolayer and the tunneling distance becomes, very, very long. Is the HPN in between the two monolayers misaligned with the graphene layers? So the answer is yes. There is no twist control between the interlayer HPN and the two monolayer graphene. Yeah, so that's the answer in a nutshell. Yeah. How do we do this? I'm not sure if I have something like this in my backup slides, but so the answer, I will try to sketch it. So if the two layers were to be misaligned, we would not see a single resonance like this. We would actually see two resonances, okay? So, and I have the data, but I didn't prepare it into this talk. So if I can draw it on this board right here. So this would be the zero twist main resonance that you see right here. So this is theta equal to 0. And if we were to have a twist between the two layers, we would see two of those. Okay, so this main resonance right here would split into two resonances, and the splitting would grow with the twist angle, which is a mismatch in momentum space. It's not too different than the picture that I described right here. So a splitting of the resonance is proportional to the momentum mismatch, which is proportional to the twist angle.
Okay, maybe one last question.
How sensitive is the Josephson coherent situation to the in-plane field?
To an in-plane field, an in-plane magnetic field?
Yes.
So it should depend on the coherence length. So if the coherence length is large, it should be more sensitive. If the coherence length is small, it should be less sensitive. I should say that we have not done extensive experiments to answer that question quantitatively. But it's supposed to be, yes, it's supposed to be, it should be able, we should be able to back out the coherence length from measurements like that. Yeah.
Thank you.
Okay, with that, let's thank the speaker.